Hi there and welcome. I thought I would make a few recordings for you to see if we could get caught up in stoichiometry. It's our current unit 6. So this will be the first one, and this is like the stepping stone to the larger problems that you had seen in class today. And so Unit 6 is all about stoichiometry, which is a way, it's basically dimensional analysis or factor label method. It's a math strategy that's called stoichiometry in chemistry because it applies to a chemical reaction. But what it allows us to do is to take those chemical reactions it sounds like you've been working on, once they're balanced, now we could take those reactions and we can use them kind of like a recipe where we could figure out, okay, if I want to make this much ammonia, how much nitrogen do I need? Or if I want to make this much magnesium oxide, how much oxygen do I need? And so forth. So it allows you to calculate what you need, what you're going to make, how much you're going to make using those chemical reactions. So again, this slide here, we often relate stoichiometry to a recipe. And so in this case, if we look at the recipe, we need 2 eggs in order to make 12 cookies. And so that's just going to be like our chemical reactions where we need 2 nitrogens to make 12 ammonias or something like that. And we can increase or decrease that ratio. So if I only have 1 egg, then I can make 6 cookies. Or if I have 4 eggs, I can make 24 cookies and so forth. So the same idea of a recipe we're going to use and apply it to chemistry and stoichiometry. And so this here is a balanced chemical reaction. It sounds like that's what you were doing. And now that it's balanced, these coefficients that you were putting in front represent something called a mole. A mole is a unit of measurement we're going to take a look at in a second that specifically applies to chemistry because you'll see it's such a big number to refer to a whole lot of really small things. But anyway, those numbers in front are what we call moles. So now I could read this equation as 1 mole of nitrogen plus 3 moles of hydrogen makes or yields 2 moles of ammonia. And once we have those moles, from there we can calculate. So we can figure out how many particles we have, how many grams we have, how many liters we have, volume, or a mix of any of those. So that's where we're headed. So starting off with the mole is, or sometimes called Avogadro's number, is that number you're seeing at the top there. It is 6.02 times 10 to the 23rd. And it could be atoms, molecules, formula units, particles as a general name. So it's used to measure really small things. So we can have billions of atoms in a really small space. And so we need a big number like this in order to talk about them and reference them, which is why you probably haven't seen them all until you get to a class like chemistry. Just like any other unit of measurement, like miles, inches, pounds, like it has here, a mole is just another unit of measurement, just like those. And so in this case, we have food, we have bagels, we have eggs, we have flowers, but what they all have in common is that they all represent, well, a physical thing, but they all represent quantities. And so just like a dozen is always 12, and it doesn't matter if I have 12 bagels, 12 eggs, 12 donuts. A baker's dozen is always 13, a half dozen is always 6. So same thing, a mole is always 6.02 times 10 to the 23rd. So again, just like 1 dozen is always 12, 1 mole is always 6.02 times 10 to the 23rd. Again, it's sometimes called Avogadro's number after scientists who helped discover it or create it. And on the right-hand side, it's based off of carbon-12. Again, just sharing that background information so you know where it's coming from. To just kind of wrap our head around the size of a mole, these are just some examples. If you wanted to produce one book with 1 mole of words, it would take 1 billion printers, each printing at a rate of 10,000 words per day, more than 1 billion years to make that book. Or at the bottom there, a stack of Avogadro's number of pennies would stretch most of the way across the Milky Way galaxy. and so forth. So it's a really big number. If you write it out of scientific notation, you could see all of those zeros up there. So again, we only see it in chemistry. I'll just pause here. I have two questions here for us to take a look at. So you could pause the recording. I'll just count to 10 and you could give them a try. So I have a dozen nitrogen atoms, oxygen atoms, carbon atoms. Which one would have more atoms? So in this case, they're all the same, right? So just like 1 dozen is always 12. So it doesn't matter what you have, it's still 12 of those items. And we're going to apply that now to chemistry. So I have 1 mole of nitrogen, oxygen, and carbon, or 1 mole of nitrogen 14, 1 mole of oxygen 16, 1 mole of carbon 14. Which sample has more atoms? Okay, so again, the answer is the same. They're all the same, right? Those numbers at the end, nitrogen 14, oxygen 16, those are isotopes. I'm sure you've seen at the beginning of the year. That's just a mass number, right? So really, it's still 1 mole is still 6.02 times 10 to the 23rd. They're all the same. All right, so now that we know what the mole is, we're going to use it as what we call a conversion factor. So I'm kind of jumping right into this. You may have seen this math strategy before when you're converting inches to miles or feet to yards or something like that. The conversion factors, factor label method, dimensional analysis is a way to convert units. We use it as kind of the basic math of chemistry, and we call it stoichiometry specifically because it applies to a chemical reaction. But anyway, we're going to start using these conversion factors or the mole and start converting units. And the reason why is because our chemical reaction we just saw is written in moles. But we can't measure moles. We're not going to go into a lab and count out moles or go into a store and buy, so many moles of ammonia or something like that. So we need a way to get from moles to grams or from moles to liters, because we can go into a store and buy a liter of ammonia, or we can buy, 3 grams of salt or something like that. So we need to be able to convert or change from the mole to another unit. And these are the building blocks to do that. So we're going to start off with 1 step dimensional analysis problems and build up to the big ones that you saw today. So a conversion factor is a way to convert between units, and it relates 2 units to each other. So in this case, our conversion factor is Avogadro's number, where 1 mole is always equal to 6.02 times 10 to the 23rd, and that could be atoms, molecules, formula units, particles, whatever. Every conversion factor can be written 3 ways. So we could write it with an equal sign in the center, like you see here, or we could write it as a fraction so that we could plug it into our problems and solve. So I could write it as 1 mole over 6.02 times 10 to the 23rd, or I could put Avogadro's number on top and put it over 1 mole. So all 3 of those ways says 1 mole is equal to this many molecules. At the bottom here is a roadmap. So it's telling you, hey, if you're given the number of moles, you would multiply by Avogadro's number to get atoms. And if you're given atoms, you would divide by Avogadro's number to get moles. So I share that with the class to start, but I'd rather not use that. I tell the students to just kind of think logically through the problem rather than memorizing I should do this or that, because by the time you get to those bigger problems like you saw today, there is no one way to do it. You have to think through and figure out how you're going to solve, and it's going to be different every time. So I do share that at the bottom when you're first learning if you want to use it, but then I would try to put that aside and just take a look at the problem and think it through to see how you would set it up. So I'm going to share a few examples with you, and then you could pause the recording and try a few on your own. So it says, how many molecules are in 1.2 moles of water? So I have 1.2 moles of water, and I want to change it to molecules. And so I'm going to start by writing the given. So the given is the number they give you in the problem. It's 1.2 moles of water, and you want to make sure you're writing out the whole thing. So don't just write 1.2. You want to write 1.2, the unit, which is moles, and the substance, which is water in this case. And the reason why is because in order to set up these problems correctly, units and substance have to match diagonally so they cancel. And so if you don't have moles there and you don't have the substance, then it's going to be hard to figure out what goes next, and it's really easy to make a mistake. So I'm going to start with what's given in the problem and then multiply it by my conversion factor. Again, I don't want to write it as an equal sign because that's not going to help us. I'm going to choose one of these fractions. I'm choosing the one with the mole on the bottom because moles of water has to cancel out with moles of water so that we're changing it over to molecules. That's the idea of dimensional analysis, to convert units. So units have to match diagonally or top to bottom. So just like a fraction in algebra or math class, if you have x squared over x, it's x, right? Or if you have, 5 over, 10 is 1/2, right? You could reduce it. Things in the top cancel with things in the bottom. Same thing here. They're diagonal because we're keeping fractions separate. You'll see why later, so it matches up to our problem. But when you're multiplying and dividing fractions, order doesn't matter. It doesn't matter that they're diagonal to each other. Just anything in the top is going to be able to cancel with anything in the bottom. So moles of water cancels with moles of water. I'm left with molecules of water at the top, which is good. That's the question. Again, this center piece is my conversion factor, Avogadro's number that I plugged in. So we have to manually cancel our units and our substance, and we've done that. So units cancel, substance cancels. And then we could grab our calculator and let the calculator do the numbers for us. And so from here, you need to multiply anything that's in the top of a fraction, divide anything in the bottom. So I'm going to take 1.2 times 6.02 times 10 to the 23rd. Of course, divided by 1 doesn't matter, and then get your answer. So how many molecules are in 1.2 moles of water? There are 7.2 times 10 to the 23rd molecules of water in 1.2 moles of water. Let's look at one more. So this time it says how many atoms. And the reason why it says atoms is because we're referring to zinc, and zinc is an atom. If we go back to the previous one, we use the term molecules because water is a molecule. So Avogadro's number could be particles, atoms, molecules, formula units, anything. It just depends on what substance you're looking at, and that's how you want to identify it. So in the second question, is zinc. Those are atoms. So I'm going to say how many atoms of zinc are in 3.4 times 10 to the 24th. That should say moles. Let me fix that. How many moles of zinc are in 3.4 times 10 to the 24th atoms of zinc? So again, I start with what's given in the problem. I plug in my conversion factor. This time moles is on the top because I need units to cancel out diagonally. Atoms of zinc is going to cancel out with atoms of zinc. Once you make sure your units and substance are canceling, grab your calculator. You're going to multiply anything in the top, divide anything in the bottom. So 3.4 times 10 to the 24th times 1 divided by 6.02 times 10 to the 23rd. We have 5.6 moles of zinc. I think I have one more for us to take a look at. This one, again, we're using molecules because glucose is a molecule. So how many moles of glucose represent 3.0 times 10 to 24th molecules of glucose? Start with what's given in the problem. Plug in your conversion factor, so units cancel and substance cancels diagonally, and then grab your calculator to solve. What you're seeing here at the bottom is, in class, I often tell the students to just put down your calculator and kind of critically think through the problem. So if 1 mole is 6.02 times 10 to the 23rd, and we have, or you could think of it the reverse, if 6.02 times 10 to the 23rd is 1 mole, then 3 times 10 to the 24th, I would change that over to the 23rd, so that you can compare. So 30, right? So if 6.02 times 10 to 23rd is 1 mole, then 30 is going times 10 to the 23rd is how many moles, right? So kind of 30 divided by 6, which is 5, and critically think through, it makes sense. Right? So as you're going through, you can think through that as well. Okay, so there's a few here for you to try. Here's the first one. I would just pause the recording, write it down for yourself, and then I will pause here myself and count to 5 or so, and then share the answer. I have 3 or 4 of them like this. So here's the first one. Here's the answer. Here's the next one. Here's the answer. All right, the next one I wanted to share with you just to be thorough. So you're not going to see this too often, but if you do take another chemistry course in college, you will. And in this case, it's a 3-step problem because they're giving you a molecule but asking you for an atom. And so the question is, how many atoms of oxygen are in 7.21 moles of carbon dioxide? And so I'm again going to start with what's given, 7.21 moles of carbon dioxide. My second step is still the same. I'm plugging in Avogadro's number so that units match and cancel diagonally. But now that gives us molecules of carbon dioxide, but the question is asking us for atoms of oxygen. So you just want to take a look at that formula. For every 2 atoms of oxygen, I have 1 molecule of carbon dioxide, right? Because there's 2 oxygen atoms in every carbon dioxide. So I could also use that as my conversion factor. And so I have molecules of carbon dioxide, cancels out with molecules of carbon dioxide. And again, multiply the top, divide the bottom, you have atoms. And so again, I'm not going to ask you to solve those, but I wanted to make sure that you've at least seen it. You may see it again, depending on what you decide to do. Here's one more. So how many atoms of hydrogen are in moles of methane? Right. So we're going to start off the same. And this time I know for every 1 molecule of methane, there's 4 hydrogens in there. And so we're going to use that as a conversion factor as well right here. And that is it. So if you would like to, I have this slide here. There's 3 questions on there, and the 4th one is highlighted because that one is the multi-step one that we were just looking at. If you'd like to pause the recording and try, you can. The next slide has the answers. And so I will count to 10 right here and flip to the next slide. Right, here's the answers. Alrighty, so there are 3 mole conversions, and we've just done the first one. So this is a good place to stop the recording if you need a break, but I'm going to keep going and do the other 2. So you don't have to listen to it all at once, but it'll all be in one place. So again, these are the stepping stones to the larger problem, and there are 3 conversion factors. We've done the first one. The second one has to do with mass. And the conversion factor for mass is something called molar mass. So we need to use that first, and then we could go back to the dimensional analysis. So what I've done here is I've taken oxygen from the periodic table and blown it up so we could take a look at that box. And at the beginning of the year, this number at the bottom, this 15.999, in class, you probably referred to it as atomic mass unit, AMU. It's a mass number. You round it and subtract the protons out to get the number of neutrons. It's also something called average atomic mass, which is the weighted average of all of the isotopes of that type of atom that exists in the world. So you may have refer to that number as all of these things, and it is all of those things. But in addition to that, it's also a mole. So that number at the bottom of the periodic table block for each element is how many grams are in 1 mole of that element. So for oxygen, there's 15.999 grams of oxygen in every 1 mole of oxygen, and that is our next conversion factor. It's called molar mass. They come from the periodic table. Also, as we go through, you may see me round these. So the more you use them, the more you just memorize them. You really don't have to use 15.999. You could just round that to 16, and all of the others as well. You can round them. So here's a look at some examples. If I wanted to find the molar mass of these elements, I would just go to the periodic table and look them up. So carbon's molar mass is 12 grams per mole, nitrogen's 14, chlorine's 35, 45, and so forth. However, most of the time we're not asked for a single element, we're asked for a compound. So if we wanted to find the molar mass of water, we would just add it up. So the molar mass of hydrogen is 1, and there's 2 of them. And the molar mass of oxygen is 16. So 16 plus 2 is 18. The molar mass of water is 18 grams per mole. And so we're going to have to do that most of the time, is to add up all of the molar masses from the periodic table for a compound to find that conversion factor and then use it. So here's an example. If I wanted to find the molar mass of glucose, C6H12O6, I'm going to start by listing out the 3 elements that I see there in the compound. I'm going to go to the periodic table and find the molar mass of each one. So sorry about that. Carbon is 12 from the periodic table. Hydrogen is 1, oxygen 16, rounded. And then I'm going to multiply by how many I have in the compound. So I have 6 carbons, so I'm multiplying by 6. I have 12 hydrogens. I have 6 oxygens. Once you multiply, you add them all up. And so the molar mass of glucose is 180 grams per mole. Right, so if you want to pause here and take another look at that, you can. Here's some for you to try. So you could try as many as you like. Pause the recording. You want to see if you can find the molar mass of each of those compounds. All right, I'm going to flip to the next slide so you can see the answers. You can double check what you have. All right, so molar mass then is our second mole conversion. Here's a look at what we have so far. So we have Avogadro's number, where 1 mole is always equal to 6.02 times 10 to the 23rd things. Those things are particles, molecules, atoms. And our second one now is molar mass. 1 mole is always equal to the molar mass of whatever that compound is. So where 6.02 never changes, the molar mass is going to change every time, because the molar mass for every compound is going to be different. So that one you have to calculate before you use it in our conversion problems. So here's an example. I have 353 grams of carbon dioxide. How many moles of carbon dioxide do I have? So the first thing I'm going to do is calculate my molar mass, because whenever I see mass or grams, my conversion factor has to be molar mass. If this had said molecules or atoms, then I could use Avogadro's number. Right? But since we're dealing with mass this time, we need molar mass. So I'm going to find the molar mass of carbon dioxide, which is what I've done over here. So I list out what I have, carbon and oxygen. I find the molar mass from the periodic table, multiply by how many I have, and then add them up. So the molar mass of carbon dioxide is 44 grams per mole. And now that becomes my conversion factor. That is 44 grams of carbon dioxide in every 1 mole of carbon dioxide. And so now, again, I'm going to start the problem the same way with what's given, which is 353 grams of carbon dioxide. And I'm going to plug in my molar mass as my conversion factor this time in a way so units cancel. So grams of carbon dioxide has to cancel with grams of carbon dioxide. That puts the 1 mole on top, which is good because that's our question. Grab your calculator. 353 divided by 44. Let's look at one more. It says how many, or I have 25.7 moles of sodium chloride. How many grams of sodium chloride do I have? So moles to grams, I see grams there, which means I need molar mass. Well, off to the side, I'm going to find the molar mass of sodium chloride, which I did. And then take that and plug it back into the problem. This time the mole is on the bottom because I'm starting with moles of sodium chloride. So I want to make sure they cancel, which puts the molar mass on the top. And this time I'm going to multiply 25 times 58 and get your answer. As part of this unit, we've done something called significant digits. And if you're really interested, you could go into the course and see, or let me know, and I can make a separate recording for that. But in this case, significant digits are the important ones when you're making measurements. They're the ones that count, sort of say, and there's rules to them. In this case, there's 3 significant digits to start the problem, so we need 3 to end the problem, and it needs to be written scientific notation in order to get those 3. Otherwise, it's going to look like we have more significant digits than we do. So that's why this particular answer is in scientific notation, but again, you don't have to worry about that right now. Okay, so here's some for you to try. You could pause the recording here and see if you can write up those problems and convert grams and moles. Right, here's the answers. Right, there's 2 other types of problems I just wanted to share with you. If you'd like to give them a try, you can. Here's the first one. And the reason why this one is slightly different is because instead of asking you how many grams do you have, it says how much will you weigh out. And so there is a difference between mass and weight. You usually don't talk about that till physics. That's where it makes a difference because you deal with outer space over there. For us in chemistry, even though there's a difference between mass and weight, we often say weight when we're massing something. And in lab, 99.9% of the time, if you're asked to weigh something, it's in grams. Most of the equipment, the scales are going to be in grams. And so when the question asks you how much will you weigh out, what it's really asking you is how many grams do you have? So if I have 2.3 moles of hydrochloric acid, how much do I need to weigh out in order to get that? So you could pause the recording here and give it a try if you'd like. Here's the answer. And finally, one last type. And this one is, again, worded a little differently. So it says, I need 4.1 moles of carbonic acid for an experiment. I weigh out 212 grams of the compound. Do I have enough? So it's really a yes or no answer, but you have to do the math to figure it out. There's 2 ways to solve this problem. So if you'd like to give it a shot before I say anything, you could pause the recording here, and I'll share the answer with you in a moment. So here's our answer. You can either start with 4.1 moles of carbonic acid, or you could start off with 212 grams of carbonic acid. It just, either one works. And so you either have to get moles to grams and then compare them, or get grams to moles and compare the moles. So on the left-hand side, I started with the grams, and 212 grams of carbonic acid is 3.41 moles of carbonic acid. However, I have 4.1 moles of carbonic acid. I apologize. So this is smaller than what I need, and therefore I don't have enough. So let me say that again. I started off with 212 grams of carbonic acid and changed it to moles. This is how much I do have. 4.1 moles is what I need to do the experiment. and therefore I don't have enough. You can also do it the other way and start with moles. So this time I'm starting with the 4.1 moles of carbonic acid and changing it to grams. I need 250 grams. I only weighed out 212. So again, I do not have enough. Okay, and that is it for molar mass. That is our second mole conversion. So this is another good spot to stop if you need a break. We're at about 30 minutes if you go back to the recording. And I'm going to go ahead and keep going and do our last mole conversion, which is volume. Okay, so molar volume is our last one. And here's a look at just some example reactions that deal with all gases or some gases. So the first one, we have ammonia from nitrogen and hydrogen gas. We have water from hydrogen and oxygen gas. And down at the bottom, we're making table salt with chlorine gas in there. And so when we're dealing with gases and chemical reactions, they can be tricky. Oftentimes we can't see gases. They're difficult to just grab and put on a scale and weigh. And so we have to deal with them differently. However, their volume is greatly affected by changes in temperature and pressure. And so this next slide here is a look at maybe some things that you may have seen over time. If you had balloons in your car on a hot summer day with the windows up and the doors closed, they'd probably eventually pop. If you had cans of soda in the back seat of your car, again, on a hot day, they could explode. If it's a really warm day right in the fall, and then the next day is a really cold fall day, temperature drops really fast. It may look like your tire's flat in the morning, but it's really not, because what's happened is the pressure has gone down because the temperature has gone down. So when the temperature goes down, the gas molecules don't move as fast, their pressure goes down, and the tire looks like it's flat. Or if you have the balloons in the back of your car on a really hot day, the temperature is going to go up, the gas particles are going to move faster and eventually pop the balloon. And so we're going to see this in our next unit. We're going to focus on gas laws. But all this slide is here to do right now is to say, hey, if you're going to deal with gases and chemical reactions in stoichiometry, you have to deal with them differently because temperature and pressure changes the volume of a gas. So the scientific community came up with something called standard temperature and pressure, which is STP. And that is a standard temperature and a standard pressure that when you're doing chemical reactions, you have to be at in order to use the volume of a gas. Because if in America I did an experiment with gases and someone in England did another experiment at a different temperature and someone in China did another experiment with different temperature, we get all different answers because the gas volume would be different at different temperatures. And so when we're dealing with gases, we want to make sure we're at STP. At STP, standard temperature is 0 degrees Celsius or 273 Kelvin. Standard pressure is 1 atmosphere. But again, that's just background information for now. We will deal with those numbers and use them in calculations in our next unit. For now, I just want to introduce it because you will see STP in the problems just to say, hey, we're at STP, so you could use molar volume and it's going to work. Our friend Avogadro helped us with this whole idea behind molar volume, and what he said is that the size of the gas particle doesn't matter because there's so much space in between gas particles. So in a solid, all the particles are packed really close together. In a liquid, there's a little bit of space, but in gas particles, they're way far apart. So it doesn't matter if you have hydrogen gas or if you have methane gas or if you have a bigger gas. The size of the particle is not going to make a difference in the volume because the spacing is so big. And so because of that, we're going to see that the volume of all of the gases are going to be exactly the same at standard temperature and pressure. Again, size doesn't matter. If I have these balloons in the same room at the same temperature and pressure, then I know these all have the same volume and I know these have different volumes, again, because we're at that standard temperature and pressure and the gas does not matter. So this could be helium in one, hydrogen in one, methane in one, and so forth, but they're all going to have the same volume because the size of the particle doesn't matter. So that brings us to actually what our conversion factor is, which is 1 mole is always equal to 22.4 liters of gas as long as you're at STP, and that is for any gas, anytime. So whereas molar mass, you have to calculate every time because it's different on the periodic table for everything, molar volume never changes, so it's an easier calculation. Up at the top there, I have 11 2-liter bottles because the volume is 22.4 liters. So if you take kind of picture 11 2-liter bottles, you can kind of wrap your head around molar volume and how big it is. Great. This is just kind of pulling everything together. So if I had 2 containers of gas, one is fluorine, one is chlorine, they have 1 mole in each of them, which means they both would have 6.02 times 10 to the 23rd molecules. They both would have 22.4 liters because 1 mole is always equal to those 2 things at STP. However, their mass is different, right? Because the molar masses change every time. All right, so that brings us then to our 3 conversion factors. We have Avogadro's number where we started. 1 mole is always equal to 6.02 times 10 to 23rd particles. The molar mass that we just finished that changes every time based on the periodic table. So 1 mole is equal to the molar mass of whatever substance you're dealing with. And finally, our third one, molar volume. So 1 mole is always equal to 22.4 liters as long as you are at STP. So we're going to take that then and plug them into our problems just like before. It's going to make our life easier because it doesn't change. So it says determine the volume in liters occupied by 0.3 moles of a gas. Notice it just says of a gas because it doesn't matter what it is. As long as it's a gas at STP, the numbers are the same. So how many liters occupy 0.3 moles of a gas at STP? I start with what's given. This time my conversion factor is 1 mole is equal to 22.4 liters. Again, I want to plug it in a way so units cancel. Grab your calculator, solve. The next one is one for you to try. So if you wanted to pause here and just kind of take another look at that one, you can. Okay, here's one for you to try. Go pause the recording, give it a try. There's the answer. And I have one more and then the recording is over. There's one more for you to try. You could pause the recording here and again, give it a try. And technically, if I forget to write STP in the problem, you can't do it, right? So in this case, we're just making sure we understand what STP is just for the fact that we're going to see it there and it needs to be at STP in order to use molar volume. But like I said, we'll do the calculations with that and so forth in our next unit. Anyway, you can pause the recording here, try this one. And here is the answer. Right, so I'm going to go back up here and leave you here with this slide. So again, these are the 3 basic mole conversions that we're going to use and string together to get those bigger problems that you saw in class today. So I'm probably going to have to do maybe 2 more recordings to get through everything. I will go ahead and email this to you. I'm also going to email you a few questions, maybe 5 or 6, maybe 2 of each for you to try, and you can turn that in. That could be your homework over the next few days, going back and forth through email until we're all caught up. So I'll go ahead and do that. You'll see an email from me soon. I guess you would have already seen an email now because I sent this to you first. And if you have any questions, just let me know.